Hello, welcome back. So today let's continue talking about support vector machine. Okay, so in the previous lecture, we stopped here, right? So the whole idea, let's do a brief review about SVM now. The whole idea is that when we do a classification problem, we want to maximize the margins between the nearest data points and the decision boundary. We want the boundary to be far away from the data points rather than being too close. Because if the boundaries are too close to the say to the two sides, then it is more likely to make mistakes. Right? If the new data points appears in a place that's just cross the boundary, then it could be a misclassification if the boundary is too close. Okay, so based on this idea that we want to marginalize, we want to maximize the margins of decision boundary, we formulate the SVM model into an optimization problem with constraints. So the quantity that we want to optimize is the distance between the nearest data points to the decision boundary. And the decision boundary in higher space, it can be it is just it is a hyperplane. Okay, it is something in 2D space. It's a line. In 3D space, it's a plane. But in a higher dimensional space, it is a hyperplane. And the task we have done in the previous lecture, what we have done is we find the mathematical expression of the distance between the nearest data point to the decision boundary expressed by a hyperplane. Okay, so basically the distance between any data point to a plane is the length of the projection from the vector, right? From the vector that points from x to xi, if we project that vector to the vector w, okay, and w is the coefficients that define the hyperplane. Okay, we basically want to compute the length of the projection in this way. Okay, and we can express this distance by making some mathematical transformations like this. And from this step to this step is tricky because we add a b and a minus on b so that we have a combination like this, right? We view these two parts of combinations. And that data x is on the plane, so this part is gone. And then we have only part left is the one before, okay? So now we use another trick which we set beforehand, okay? So we make sure that for the nearest data points, then the value of this expression or this expression is 1, because that's the limit we set. Without these additional constraints, the hyperplane can have infinite number of expressions. Right? We can simply multiply one expression with a constant number, can times 2, times 3, times 4, and that still give us the same hyperplane, which are of the same shape, right? But they have different expressions. So in order to avoid the infinite possibilities of expressions, we must have these additional limits that to the nearest data points, this expression must equal 1. So of course, this 1 equals 1 is also an arbitrary choice. We can also say we can always choose 2 or 3 or 4 or any kind of values as long as it is a constant number that we set. Okay, so we use a constant as a constraint so that the expressions are fixed. It doesn't really matter that which number we use, but we use 1 because it's for simplicity. Okay. So with this constraint, then the distance becomes a very elegant form in such a way. It is 1 over the norms of the coefficients of the decision boundary or the hyperplane. Okay. So now the optimization problem becomes that we want to maximize this term. We want to maximize 1 over the norm of W, which is equivalent to minimizing the norm of W, right? Because W is on the is the denominator, right? So the whole thing becomes this. We want to minimize the norm, while the norm is defined by the dot product between two vectors. Now, when the dot product is between the vector and itself, we're basically computing the norms, right? So we are minimizing the dot production between W and itself, subject to the constraints that for any data points, the value of yi times W transpose times xi plus b must be equal to or greater than 1. Okay, and only for the nearest data points, okay, that are closest to the decision boundary, this term or this expression has a value of 1. In other cases, they are larger than 1. So it becomes a very typical optimization, constraint optimization problems with constraints in the form of inequalities. Remember, in the previous class, we have a simple example showing that when the constraints are equations, it's easy to apply Lagrangian multiplier or to construct a Lagrangian term, and we take the derivatives of the Lagrangian with respect to the original parameters and the Lagrangian variable lambda. Okay, and in this case, when the constraints are inequalities, it becomes a little bit more complex. Okay, so let's carry on to the next few steps. So given our task here, we convert it into a Lagrangian duality problem. Okay, that's following the preparation knowledge at the beginning of the slides. Okay, we need to construct the following Lagrangian. Yeah, the slides are already on Canvas. Well, let me double check. Okay, I will stop recording. Oh, yeah, I guess it's easier to have the slides at your hand while watching the animations here. So we basically want to construct the following Lagrangian. Okay, here I put the target. That's our target. That's our constraints. And a Lagrangian means it's just a multiplier. Okay, we call it alpha. Okay, now it's not lambda, but it's actually the same function. And one thing we notice is that we have multiple alphas because this constraint, it is actually m constraints. We have multiple constraints. It's not a single constraint. So we have m of such inequalities. So for each inequality, we need to have a multiplier, which is alpha I. So the superscript I corresponds to the ith inequality, all right? And thus we need a summation because we need to sum up all the m inequality constraints, okay? So the thing after the summation symbol is the Lagrangian multiplier that we have constructed, okay? And we call this whole expression as a Lagrangian. And this is the new quantity that we want to minimize, okay? So because we introduced alpha, we put an alpha here, and this alpha is a vector that indicates all the alphas here used in this place, okay? So now this Lagrangian is something we want to minimize with not just with respect to W and B, but also a new variable alpha, okay? And also we have one more constraint that's the alphas, all the alphas we needs to be maximum needs to be over greater than 0. Okay, and it is called a duality problem because it's a minimize maximize problem. We are basically maximize with respect to alpha, but minimize with respect to W and B. Okay, so why this works, why it is a minimize plus maximize problem, we have basically shown it in the preparation stage of this lecture. Okay, all right, then given the minimize or maximize problem, actually it's the same thought process we need to take, right? We want to find the minimum point or the maximum point of some function. We basically need to take derivatives, right? So first, we want to minimize with respect to W and B. So why not we take the derivatives of L, of the Lagrangian, with respect to W and B, okay? And it's actually quite neat its results after we take the derivatives, because notice here, right? The vector dot product form 1/2 times W transpose times W. If we take a derivative with respect to W, consider W is a vector, then we can write derivative into this form. It's quite similar to the derivatives of scalar numbers. You can think of the W transpose times W as analogy to a quadratic term, but in this case, it is a vector variable, okay? And
Professor, I have a question. So for the minimize the Lagrange kind of equation, why the summation? Before the summation, there is a minus sign. Kind of like it's a little bit difficult to understand because the constraint about the following expression is all greater than one, right?
yes,
So and when we add a minus sign over there, it means that the summation of them is less than or equal than negative m.
mhm,
And when we say some number less than or equal to some number, how can we really do the minimize the whole equation things? Can you try to explain that? Kind of like a little bit logic confusion for me.
mhm. So we are basically try to maximize the whole thing with respect to alpha. So when this term here, when yi times W transpose times x plus b minus 1 is greater than 1, then this whole thing is greater than 0, right?
Yes.
Yes, if we want to maximize with respect to that, then the alphas will basically turn to 0, will be pushed to 0 if we want to maximize the whole Lagrangian. And that is the results that we want to achieve.
Okay, yeah.
And when this term is 0, then alpha doesn't actually matter.
Okay, yeah, that makes sense. Okay, yeah, correct.
Yeah. So that is the result we want to achieve. And we'll basically later on, we'll find that when alpha is 0, then those data points are the irrelevant data points. And when alpha is positive, and those corresponding data points are the support vectors. All right. And I think there's a supplementary link in the slides that will give more information about how the Lagrangian duality problem is constructed, and it's really complex problem, which is beyond the scope of our discussion here. All right, so now if we take derivative with w, we want it to be 0. Okay, that's what we achieve, because within the summation term, we have alpha I times yi times w times x, and that is the only term we have that has w contained. So what's left is the coefficients alpha, y, and x. That's why we have a term here, right? And then we take derivative again with respect to w, okay? And with respect to b, because the only term that we have b is here, right? Let me use another color. The only b we have is here. And the coefficients with b, associated with b, is y and alpha. So that's why the only thing left is here. And we also want the derivative to be 0. Okay, so now we have two equations. We can substitute back to the original term of the Lagrangian that we constructed. We can substitute the term back here, okay? Because we know that the w should equal this term, which we can easily plug into the Lagrangian, so that we can basically eliminate all the w and b, and the only variable that's left is the alpha. Okay, so you can use this link to know more about, to read more about the Lagrangian duality, how it is constructed. All right, so let's do the substitution, right? And into the original Lagrangian, we will have something like this. Okay, we have only alpha left. Okay, so here, this one is the result of replacing w's with this one. And w becomes the summation of alpha times y times x. So we have w times w, or w transpose times w. So now we have the nested, this two-layer summation, in which each term is wi times yj, alpha I times alpha j, and x transpose times xj. Okay, so that's something we have within this two-layer nested summation. And that's the results of this first term. And for the second term, okay, if we observe clearly, you can also easy to find that when w is plugged in here, there should be also something like alpha y times alpha y times x and times x. Okay, so, and there's a negative preserved. The negative is preserved here. The negative is preserved here, right? So that's something we should have after w is is substituted into the original Lagrangian, and we have the b terms, right? The b terms left. So for the b term here, the b is here, and the coefficients between before b is alpha and y. Okay, so that's why we have the two terms left here. Okay, so that's the term containing b, and the last term is the summation of all the alphas. Okay, so now we can further simplify the terms. Okay, because we know the summation, this term is 0, so this term is gone. Okay, and the beginning two terms can be actually merged, right? It's just the difference between the coefficients, 1/2 and -1. So eventually we have something like this. The coefficient becomes -1/2 and the summation term. Okay, so this is something looks like a quadratic function, right? Because the alphas, we have alpha I times alpha j, and here is a linear summation of all the alphas. So it's a quite typical simple quadratic form of alphas, right? Although there could be a lot of possible combinations, because here the superscript j iterates from 1 to m, and the I iterates from I to 1 to m2. So basically, we are constructing a very large matrix that the row ranges from 1 to m, the column also ranges from 1 to m, and we are trying out all possible combinations between alpha I and alpha j. Okay, so here this term basically, the quadratic term basically contains all possible combinations of the quadratic combinations between across alpha I times alpha j. Okay, so given this very simple quadratic form with respect to alpha, right? So the Lagrangian becomes this one. It is a quadratic function that we want to minimize, and actually we want to maximize with respect to the alpha. Okay, and it also makes sense, right? Because the coefficient between before alpha, it is a -1, right? It's quite it conforms to our common sense that if a quadratic function has a negative term, has a negative coefficients before the quadratic term, we are able to find the points that maximize the function. So now we basically want to maximize it with respect to alpha, and the alpha needs to satisfy the constraint that they should be positive numbers. Okay, and also there is a constraint that we need to carry, which is here. Okay, so this normalization term, basic normalization term, that is will be a useful condition that we use to compute the b and w's. Okay, so that's it for the substitution step. So what's left, we give it to softwares, because it's a very complex quadratic term here. We want to maximize it, right? We then further flip around. We times the -1 of the original Lagrangian, then it becomes minimizing this function, this flip around the reversed function, right? with 1/2 times the quadratic term minus the summation of alphas. Okay, so if we expand it, right? If we look at each term within this two-layer summation, we can express it with a matrix multiplication. Okay, so think of the alpha, okay, as a vector, because if you closely look at the alpha here, it is a summation of all possible alphas, and then the superscript ranges from 1 to n. It's basically the dot product between the unit vector and the long vector alpha, right? We have m components in the vector alpha, from alpha 1 to alpha m, okay? And this two-layer summation can also expressed by this matrix multiplication, okay? In this case, the alpha transpose is a pretty long vector here, a row vector, and the first component is alpha 1 and alpha 2 until alpha m, okay? And the thing in the middle contains all the basically all the coefficients computed from y and x, okay? So this matrix in the middle must satisfy that it has m rows and m columns, right? And the alpha here is a column vector, okay, which also have m vectors, m components in the vector. So that's how we obtain the Lagrangian, or express the Lagrangian with matrix form. Okay, so if we write it in a compact way, right, then we can rewrite the Lagrangian into this form. Okay, we want to minimize the function of 1/2 times alpha transpose times some big matrix Q times alpha minus alpha times the minus 1 transpose times alpha. Okay, and also we rewrite the one of the constraints into the dot product form as well. Okay, so this constraint is actually the summation of y superscript I times alpha I. Okay, so that is, so this whole term is just the dot product term. Okay, so we basically come up with a pretty neat form, pretty neat simple form expressed by matrices, and this Q in the middle. Okay, so everything else. Okay, so in the quadratic term, the Q is the only thing we need to compute from data. Okay, because Q is this form, exactly this form. It's a combination of y's and x's, right? If we look at the first column, it is yi times y1 times xi times x1 times x1, right? Until y1 times ym times y1 times xm, okay? And the second row is for y2, and the last row is for ym stuff, okay? So this whole matrix is from the data. So given any data, you're able to immediately construct a large matrix. It looks like the covariance matrix given the data sets, but we're not actually using talking about variance here. We're just using a bunch of dot products. We're using dot product between all the features and the product between all the labels. That's how we construct the Q. Okay, so Q is something we can compute, right? It's pretty clearly defined. So after all, now this type of optimization problem, we can feed it into some softwares that solve the quadratic programming problem. Okay, so the quadratic programming or QP software will output the alphas that minimize the target function, the target Lagrangian. Okay, and now the W's, when W is returned, or when the alpha is returned, we can compute the W in this way, because this is what we get after we, in the first step, after we first take the derivative of L with respect to W, and we let it to be 0. That's how we get this term. Okay, so after alpha is known, then we can know W, and the B's can also be known, right? So one thing we will observe after we solve alpha is that we will find that the majority of the alphas are zeros, okay? And only some of them are greater than 0, okay? So this term, the alpha times yi times W transpose times xi plus b minus 1 is always equals 0. Because when alpha is 0, those data points, so for alpha is 0, the term in them here, the internal term here, they are greater than 1, and they are farther away from the boundary. And for alpha that's greater than 0, then the inside term is 0. Okay, and they indicate the corresponding data points to alpha that's greater than 0 is exactly the data points that define the margins. Okay, so these axes, these xi's that correspond to the condition of alpha I is greater than 0 are the so-called support vectors, because they are basically closest to the margins, and they help support the this helps support the decision boundaries. Okay, and that's why we the whole method got the name support vector machines. Okay. All right. So if we visualize it in a simple data sets, eventually we will, by minimizing by solve the quadratic programming, by use QP to solve the minimizing problem of with respect to alpha, we're able to identify the support vectors. So in this case, the 3 data points here in red dotted circles, they are the so-called support vectors. Because they are closest to decision boundary, and to them the alpha is greater than 0. Okay, they satisfy that the yi times the yi times W transpose times xi plus b must be 1. Okay, and for alpha equals 0, that's the majority of the data points. Because of the majority of the data points, they are likely to be non-support vectors. Okay, only a small part of data, they are close to the boundaries. Okay, so for those alpha equals 0, they are non-support vectors, and for alpha that's greater than 0, they are for support vectors. Okay, so we can basically simplify the computation of W by only consider those data points that are within the support vector sets, because alphas, the majority of them will be 0. Okay, so that's how we get the W quickly. Okay, and we can solve the b's using any support vector, right? And to substitute them into the equation that a support vector satisfied, and then we can solve b. Okay, because w is known, and x and y, they are from the support vector, they're also known, and then b can be solved. Okay. Okay, so that's basically the final step, how we get w and b after alphas are obtained. Okay, so now I would like to do a recap of the previous steps. Okay, so we start from defining the problem of finding the decision boundary that has the maximum margins. Then we set additional condition to make the representation of the decision boundary to be unique, right? And the decision boundary is that for the nearest data points, we must have this term satisfied. Okay, and then the margin becomes 1 over the norm of w, which can be maximized. Okay, but with constraints. Okay, so we minimize the dot product of w subject to the inequalities constraints, and we have a bunch of inequality constraints. Actually, the number of constraints is the same as the number of data points. If you have 1,000 data points, you have 1,000 constraints. Okay, so we need to use Lagrangian multiplier or Lagrangian duality problem to solve it. Okay, so we construct a Lagrangian by this form using m alphas. Okay, each alpha corresponds to 1 data point. It's a duality problem. We need to minimize it with respect to w and b and maximize it with respect to alpha. Okay, so this problem can have a compact expression using matrices. Okay, so we express everything with matrix after eliminate w and b. Okay, after eliminating wb in this term, we become the Lagrangian of purely alpha. Okay, with respect to the conditions, and this is the final form that we get, and then we use softwares, use numerical methods, which is basically iterative methods to solve such alpha, and we have the solution for alphas. So for those alphas that are greater than 0, that are strictly greater than 0, we would have these are the so-called support vectors, and with the support vectors we can compute the w and b so that the decision boundary can be drawn. So that is the basic steps for the basic support vector machine. Because I said basic because in the current case, the support vector machine assume that everything can be perfectly classified. There's no misclassifications, right? There is no, if you look at the previous, there's no blue dots over here, right? There's no yellow dot over here. So there's no classifications. And we assume that a decision boundary can always find that perfectly that can perfectly split the data, the two classes. Okay. And actually that is just too ideal. And if we want to set up this ideal goal, then we have the risk of overfitting, right? If the model is trained in such a way, then the decision boundary that we obtained will try to perfectly classify all data points, right? Which is a very serious overfitting problem. So we will need to tolerate some cases that the data cannot be perfectly classified. So that's something we will discuss in the next slide.
Professor, can I ask a question?
Yes.
Picture. So if I'm understanding this picture right, is it kind of saying that, you know, there's orange dots and blue dots, and our machine is trying to classify, you know, what category they're in, and it looks like most of the dots are pretty clearly one or the other, but then the ones on the dotted lines are sort of nearer the margins, and that's why they're helpful, because I guess they're closer to the margins, so they help us kind of delineate what are the edges of, like, you're a blue dot versus you're an orange dot. Is that kind of conceptually right?
Yes, that's correct.
Okay.
Yeah, I think your statement is quite clear, because given the data points of any shape, if we have two clusters, we can always draw a decision boundary. Give me a second. Okay, sorry, I was interrupted. So I was saying that given the two clusters of data points or multiple classes, it's always possible to draw the boundary, right? But we want the boundary to have maximum margins. So we need to use some of the data points to help define the margin or define the decision boundary, so the margins are maximized. And the data points in the dotted circles, they are the points that play such a role. They are supporting the decision boundaries. Okay. Thanks for the comments. So in the next step, we're going to consider some more complex cases that the not all data points are possibly are necessarily can be perfectly classified into two very cleanly defined decision boundary. So we're gonna see how we handle these misclassifications. Okay. Actually, the bullets kernel method is not precise, because we're not going to only talk about kernel method. The kernel method is just one technique that helps deal with the deal with the case that the data cannot be linearly separated. Okay, so we're gonna look into the details. Okay, so the problem is that some data points, some data sets are not linearly separable. So if we have data set like this, right, it seems it's just impossible to draw a linear line to split the two classes, right? So what we could do is that we apply a non-linear transform to data, right? We try to apply some transformations so that all the blue dots are transformed to one cluster, and all the yellow dots, they transform to the other cluster. And in this transformed space, we can draw some linear line. Okay, so we have a boundary in this transformed space. And what we can do next is to transform this boundary in the new space back to the older space. Okay, so in the older space, we will have a non-linear, in the old space, we will have a non-linear decision boundary. Okay, so that is some technique what basically describes. So these two, the simple demo here basically describes what a kernel method will do to a non-linearly separable data sets. Okay, so I have a more concrete example here. For example, in the 2D space, we have two features, x1 and x2, right? If we have two classes, then we can basically construct or apply some nonlinear transform by subtracting x1, by subtracting 0.5 from x1 and raised to the power of 2. Like, it's basically computing some distance, some Euclidean distance, right? That's how we get z1 and z2. Okay, and we have a new Z space constructed. Okay, so in this Z space, all the red colors dots on the left, they kind clusters to the upper space here. Okay, because this minus 0.5 minus 0.5 is basically measuring how far away these data sets are from the midpoints, because the 0.5 is here and 0.5 is here. So all the green dots, they cluster here. Okay, so if we draw decision boundaries, it'll be like this, and we can map the decision boundary back. It'll be kind of a circle. Okay, so that's a pretty practical technique in the case that we know the data are not linearly separable. Okay, and later on we'll see that this method can be extended to a more generic cases, and the exponential term not necessarily to be true, but it could be to a arbitrarily large. It could be a basically any number that we can try. It could be a so-called hyperparameter we can tune. Okay.
Professor?
Yes.
Am I correct in saying that in regards to classification problems, we always want our decision boundary to be linear because it maximizes our margins? Is that why we're applying these transformations?
Yeah, because the method so far in the previous slides, the SVM model that we introduced define the decision boundary in a linear function, in a way of linear function. So the decision boundary is W transpose times X plus B. It's a linear form, right? It's a linear combination between the coefficient W and the feature X and the intercept B, okay? But if the data is not transformed, say if our X looks like this way, then if we draw a boundary in the original space, there's no way to draw linear lines that separates all the data parts, right? So we basically need to transform to the Z space. And in the Z space, we simply don't look at X, but look at Z's, and we can construct some linear decision boundary like W transpose times Z plus B, okay, equals 0. We can find something like this that maximizes the margins here, right? The margins here is maximized. And this one, we will need to, after this is done, we need to transform the decision boundary here back to the original space. So for the multiple categories of data, yeah. So for multiple categories, what we can do is a so-called one versus or one against all strategy. Like if we have data that have 3 classes, 1 and 2 and 3, then we can basically do 3 steps. We first predict 1 against 2 and 3. And in that case, we view 2 and 3 as zeros. And then we build a second model that predicts 2 from 1 and 3. Okay, and 3 against 1 and 2. So basically need to build 3 models. And after we have the 3 models, we just combine them. That tells us that will basically predict which one of the 3 classes that a new data set is given. So yeah, and it not just works with SVM, but also works with any binary classification models, say logistic regression, right? we can build one logistic regression for this one, and the second one for this task, and third one for this task. That is basically one against all strategy. Okay, so let's now continue with this step. So if we use z instead of x, then our problem of the original goal of SVM is to maximizing this Lagrangian term, right? And we notice that the coefficient that deals with x is here. Now we need to convert the dot product between x into the dot product between z's, right? Basically, we want to replace it with the z's, right? Because we are dealing with the data in a new transformed z space. Okay, so it could be of higher dimension. The z space can be of higher dimension than x. Okay, although in the previous example we are showing that z and x, they are of the same dimensional, but z actually can be of higher dimensional. Okay, for example, in the 2D space, originally the product between two 2D vector is like this, right? And we can have a higher space data sets. We can convert, say, the x into the z's that have 1000 dimensions, and x into a z of 1000 dimensions, and we still can compute the dot product between them. Okay, it's just m inner products or dot products we need to compute. Okay, and the number of data points does not change with the dimension. That's all we need to know, because the q, the number of combination, the number of product combinations is m by m. Okay, and this m by n combination is not changed with the dimension of the z's or x, right? So that gives us some convenience in choosing what kind of z space we want to use, or what kind of x to z transform we want to use. Okay, no matter how large the z space is, how many dimensions are there in the z space after we do the transformation, it remains the same optimization problem. It is the same optimization problem that we want to use for solve the SVM problem. Okay, so we are good. We're happy with this because it gives us a lot of freedom in choosing what kind of z transformation we want to use. Okay. Okay. So for example, the x space looks like this, and actually the support vectors, they are found in the z space, not in the in x space, because after we find the linear boundary in z and transform it back to x, it's not necessarily a linear form. It's usually a nonlinear boundary. It may look like this, and in the sense of a decision boundary, this one may not look like a boundary that maximizes the distances between the support vectors. Okay, so these vectors, they are not the support vectors in x space, but actually the support vectors in z space. Okay, and that's something I want to emphasize here. So the final support lines that the decision boundary that we draw in the X space is actually a pre-image of the support vectors in X space. Okay, the margin is maximized in Z space, but not in X space. Okay. So next, let's look at some further examples of what kind of Z transform form we can use actually. Okay. Yeah, so that's a good question. How do we determine for more than 3 dimensions then? So we actually don't need to know the specific type or specific form of transformation, okay? Because all we need to know is the existence of such a transformation, or the existence of the dot product, okay? Because the dot product is everything we need to know in order to construct the Lagrangian, okay? So for example, here, that's a Lagrangian we want to construct. So all we need to know is the dot product between Zi and Zj. And all the constraints, they have no requirements on Z, okay? So we can solve the Z space using quadratic programming, like what we did in the X space, okay? We can solve the quadratic programming in Z. For example, pay attention here with the X's are replaced by Z's. Okay, the Z's are actually here, not X's. Okay, after the alpha and W and B's are solved, we can have the decision boundaries computed here. So we only need to know the dot product between Zi and Zk, but like any 2 data points in Z space. That is a dot product or inner product. We don't need to know exactly what the transform X to Z is. Okay, so in the previous example that we transform a linear line, we transform a circle to a linear line in Z space. We know the exact form of transformation. It's a quadratic function, right? But actually, we do not need to know that. We can actually conduct much more free form of transformation, not necessarily quadratic function or polynomial function. Okay, so the existence of this space is sufficient. We don't need to know what space it is. We just need to know the inner product. Okay, so next we're gonna see how much freedom we've got in terms of choosing the Z transform or in choosing the Z space. So consider the 2 data points in X space, X and X prime. Okay, that's 2 data points. And we need some new inner product in Z space. That is Z transpose times Z prime. Okay, so for example, we can use some arbitrary function, capital K of X and Y, to indicate that dot product or inner product. Okay, so that's the function what we call a kernel function. Okay, that represents some type of inner product between X and X prime, but we don't know what exactly that type of inner product is. Okay, we just know that it is some type of inner product. So for instance, if the X is in 2D space and X prime is also in 2D space, right? Then for instance, we can take the second order polynomial transform phi, right? Like this one. We can say Z of Z is defined by the phi of X, and phi is a polynomial transformation. It gives us a Z in such a form, right? It has 1, 2, 3, 4, 5, 6 dimensional space. Okay, so that's the Z that we know here. Okay, and the Z prime is also 6 dimensional, which is 1, 2, 3, 4, 5, 6. Okay, so that's the result after we knowing that it is a polynomial transform phi. Okay, so the resulting dot product or inner product between Z transpose and Z prime is simply the dot product between these two vectors, right? Which is 1 plus x1 times x1 prime plus x2 times x2 prime, blah, 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 okay? And this is exactly a inner product that we want to use, okay? So we can basically compute a kernel function without knowing the transformation, okay? Say we don't know if we don't know these steps, we don't know the phi, we can also have the kernel defined, right? Purely on X. If we define the kernel function in this way, then we can claim that it is based on some nonlinear transformation defined by phi. But that really doesn't matter because we can compute kernel, and kernel represents some sort of inner product, right? So we can actually do this without explicitly knowing what a phi is. Okay. So next we're gonna show a more extreme example. Consider the form. The kernel function is defined this: 1 plus the original inner product in X space, then raised to the power of 2. Okay, so it's just a function, right? It's a function that we can use. We don't know if it is the inner products in any other space yet, but we're going to show that it is true. For example, if we expand this term, then it'll give us a bunch of these terms, right? We have the 2's here, which basically shows us it is still an inner product, because if we do such a X to Z transformation so that the X is transforming to this form with square of 2 as its coefficient, and also X prime is the X prime is transformed to Z prime with also X square root of 2 as a coefficient. That'll give us the Z and Z prime. And if we examine Z, the inner product between Z and Z prime, it will give us the inner products, the form of the kernel function. Okay, so this is to show that any kind of kernel function in this quadratic function in this form, we can think of it as a inner product between two Z vectors. It's not necessarily true. The kernel function can be higher order polynomial terms or even exponential terms. We'll show later about the higher order polynomial function term. Okay, so that's what we call a polynomial kernel. Okay, we are basically transferring X into some polynomial higher order term, but we don't need to know the exact form of the polynomial transformation. Okay, the equivalent kernel, we just need to know the kernel, right? The kernel is decided by 1 plus the inner products in X space raised to the power of Q. And this kernel represents the inner products in Z space, okay? But we don't need to know what the exact Z space is. Here we will show that if we do this within a D-dimensional X space, okay? This is a rather simple computation, okay? So it's just a sum of D products, okay, and then raised to the power of Q. We don't need to exactly expand the polynomial term because we want some numerical results out of this kernel function. Okay, we don't need to expand the Q order polynomial term. Okay, and also this polynomial kernel can be adjusted by some further hyperparameters defined by A, defined by B. That's something that we can tune by the in order to find the most suitable polynomial kernel function. Okay, so actually we can even know less about the Z space. Okay, we only need to know Z exists. We don't need to know whether it is a polynomial transformation or not. Okay, so for example, this radius basis function RBF kernel is to use the distance of the between two data points in the X space. Okay, it's the L2 norm or the Euclidean norm times some gamma, which is the hyperparameter, given negative, and then raised to the power of e. Okay, so that's the exponential function. That is some kernel we can use. Okay, and this kernel also represents some inner products in a higher dimensional space. And if we expand this term, say if we look at the 1D space in X, 1D space, the X is in the 1D space and the gamma is 1, then the kernel function becomes this, right? And we can expand this term a little bit, and we can further expand this term. If we use the Taylor expansion of it, because the natural base raised to the power of x can be expressed by the Taylor expansion here, and if we replace it into the original term here, we can see it's actually a bunch of summations. Okay, and within each item of the summation, we have x raised to the power of k and the x prime raised to the power of k. Okay, and we have an infinity here because it's Taylor expression. So this says that this is actually a form of what? A very long inner product that belongs to a infinite dimensions. Okay, so with so much complex math here, with the Taylor expression, with the different highlight colors here, what I want to show is that this is no more than some inner product. Okay, but we don't need to know what kind of Z space it is. We just need to know that the kernel function in such a form, the exponential of the original distance in X space can be some can be used as the inner products of some higher dimensional space. And actually the dimensions actually infinite number of dimensions. Okay, so RBF kernel is more is often used in the case of building SVM models. Okay, so I think I will finish this slide. So going back to the problem of solving the SVM's target function, which is to maximize this quadratic term subject to the condition. Previously, we have the x, it's in X space, right? Now, after we use kernel to convert X to Z, we will have something like this. We have k of the X and of the different combinations of X's, okay? So we just replace the original inner product with the kernel functions, and everything else is the same, okay? But the solution after we the return by the quadratic programming function, the alphas, they point to the support vectors in the Z space, okay? So I think we're gonna skip this. Let me finish these 2 slides, okay, and then we're done with today. Okay, so when we solve the SVM with kernel functions, we just replace x with z's. Okay, after we have solutions that return a bunch of positive alphas, they represent the support vectors, and then we can use them to solve the W. Okay, and decision boundary in Z space is W, and it is actually the alpha times yi times the kernel functions. Okay, so that's the decision boundary in Z space. So the inner product is something we can compute very easily because it's just a numerical function. And then we can compute the B, okay, because the support vectors needs to satisfy that this term for the B terms. Okay, and the model is basically this way, because we just need to look at on which side of the district boundary that a new data point is. Okay, if it's on one side, then it belongs to the one class. It is on the other side, it belongs to the other class. Okay, and next slide. So this will be something that we'll cover in the next class. We have not many slides left, so in the next class on Thursday, we'll finish the support vector machine by talking about using some soft margin to deal with misclassification cases, to give more tolerance to the misclassifications. And today we have used the kernel method to solve the data that are more horribly non-linearly separable. Okay, and combining these 2 methods, SVM is a very powerful approach to find a reasonable decision boundaries without causing too much overfitting to the original data sets. Okay, so that's it for the course today, and I will release the video and the quiz questions because last time I don't release quiz questions, and this time we'll have 2 or 3 quiz questions released, which will be due on Friday. Okay. Let me stop recording here.